This is a vector space. Do you agree? Okay. Now, what is the basis of this? 1 x squared. These are bases, right? Because I can get any polynomial by linear combination of these three, and these are linearly independent. So, what is the dimension of this vector space? Is 3, right? Because only 3 vectors suffice. Clear? Now, what is the subspace of this? Any idea? What is the subspace? Let me call this as P1, which is alpha naught plus alpha 1 x such that alpha naught alpha 1 belong to R. This is subspace, right? Do you agree? Because I'll pick A2 to be equal to 0 in the previous, I'll get all this. So it's a subset. Now, how do I prove that it's a subspace? Well, you take any two combinations of this first order polynomial, I'll get another first order polynomial, right? I cannot get second, second degree polynomial, not R, right? So it has to be a subspace. Is that fine? Clear? Okay. So this is a mistake that we did, right? So I tried to give a fancy, example of, the coefficients being rational and all that. No, I mean, this is a simple one. We need not worry too much about this. Okay. So now, of course, we have the notion of subspace, and we'll just looked at what is a transformation or a map, right? Matrix is a simple transformation. So you can have any other transformations. So now let's look at what are the possible properties of a matrix transformation. Okay. So let's take a map which is from, let's say, Rn m to Rn. This is a matrix. Okay. Now, what can you say about this transformation? First thing is, if I take two vectors, right? Let's say I take u and v in this vector space, right? Two m-dimensional vector. What can you say about A times u plus v? Of course, it's in Rn, that's for sure, because u plus v is in Rm. Rm is a vector space. If I operate here, by definition, it goes to Rn. But I can write this, right? Why is this true? Well, exercise. Take an m cross n matrix, x plus y, ax plus a times x plus y is ax plus ay. That's very clear. Okay. Now this also belongs to Rn because by definition of A. So what is this property called? Okay. Now let's say I take u multiply by a number alpha. Okay. So I'm going to scale it by alpha and operate A. What do I get? Right? It's like operating A on u and then scaling it by alpha, right? This is also very straightforward. So if you can you recall some name for this? What is this called? What is this called? Any idea? What is this called? No idea? Hey, you should have learned this in. How many of you are in? Most of you are in third year, right? So you have taken control systems, at least electrical engineers, signal systems. Okay, now you should tell me. At least electrical engineering students should tell me the answer. What is this called? I can't hear you. Linearity, right? It's called linear. Okay. It's called linear system, or it's a linear transformation, right? So how do I generalize this? So you take any T that maps a vector space V to a vector space W. How do I define linearity? Same old stuff, right? So what do? I take UV in V and take alpha in R. Let's assume that these vector spaces are defined over R, right? Now, all that I have to do is, u plus v is tu plus tv, and transformation of alpha u is alpha times transformation of e. This is how we define linearity, right? Right? Okay. So now it doesn't matter. Now I can sort of mimic matrices by using transformations. So why do you need transformation if you have matrices? The answer is, I mean, why do you need to have linear transformations if you have matrices? Well, matrix is one aspect, right? So for example, if you are dealing with R and Rm, fine. But what if you are dealing with something else, some strange vector spaces, right? For example, set of all continuous functions from 0, 1 to 0, 1, right? That forms a vector space. So what is the guarantee, right? So how do you deal with transformations there? So what is a transformation there? Can somebody tell me? Suppose I say V is set of all 0, 1 to 0, 1, okay, such that, let me also make one more simplifying assumption, equal to 0. So how does this functions look like? Let's say this is 1 and this is 1. It's like all sort of functions like this, all kinds of functions, right? Right, all kinds of functions like this. Well, it's 0, 1, right? So is this correct? No. Why? Negative, I mean, that's an issue, right? It cannot be negative. So let me redraw this. It'll be like this, right? 1, 1. Okay. Assume that its peak is 1. All kinds of functions like this, right? Each function is a point in the set, right? So you have uncountably many functions which I collect in a basket called V, and this is a vector space. We saw that, right? Now, what is a transformation here? Any idea? Weird, right? So what do you mean by a transformation of this? What is a transformation, for example, from V to V here? Can you give me an example of a transformation? Just to, I'm giving these examples just to make things clear, okay? So vector space means not just Rn. There are other examples, and it will be useful in general, okay, even in machine learning or data analysis. What is a transformation? In the usual stuff, matrix, it takes a vector and gives you a vector, right? Here, what should it take and what should it give? You should take a function, should give you another function, right? Can you give me an example of such a transformation? It takes function as input and functions as output. I think electrical engineering students should be able to give it. I think even mechanical, right? So you would have seen so many, huh? What is that? Okay, so let me give you an example, right? You take a function f of x. I will integrate dx from 0 to 1 because f of x is defined from 0 to 1, right? This is a transformation, right? Why? This is some other function, let me call it as psi of y, right? Because for each y, you'll get a number. So it's psi of y. One thing is this y should be in 0, 1. Is that good enough? No. Why? Because I want this also, right? So I should ensure that psi of 0 is 0 and psi of 1 is 0 again, right? I should choose such a function g of xy. Then it's a valid transformation. Fine? Okay? Is this okay? Now the question is, can it be linear, right? So let's not go deep into this, okay? So we can come up with an example where t is linear even here. So now, what is the importance of this, vector space business or linear algebra? It unifies things, right? On the one hand, you can look at vectors, discrete. On the other hand, you can look at integral equations and so on. All these things can be solved in one umbrella, right? One textbook will kind of solve many of these problems, right? Okay, so now we have the notion of transformations and we have the notion of linear transformations, right? So now let's go back to this question of when can you invert, right? So, but what do you mean by inversion? So for example, I have a vector, let's say mapping from, let's say V to V itself, okay, for simplicity. So what do you mean by so a transformation being invertible? Of course, linear transformation from now onwards. I won't look at non-linear transformations. So what do you mean by invertible? Can somebody tell me? What do you mean by invertible? So it essentially means this. So suppose I write it pictorially. Suppose this is my V and V. Suppose I give you a vector here or a point here. So I should be able to map to a unique point here. Do you agree? That means a point in the range. So this is called range. What is this called? Domain, right? Yes. So now I give me any point in the range, I should be able to find a unique point in the domain, right? That's one thing. Is it good enough? Suppose I give you a point here, nothing gets mapped to this. Then also it's a problem, right? I don't know how to invert that because nothing gets mapped to. So in other words, the range should be the entire vector space. These are the two things. What are these? There are names for these things, right? No big deal. I mean, intuitive. If you let's say if you had born in the, some 1300 AD or something, maybe, or you would have invented the same thing, right? What is the name? A unique point in the range maps to a unique point in the domain. What is that called? 1, 1, right? Okay. What is the other thing called? You should map to the entire range. If I, right? There is another name also. Do you know? Okay. Surjective. Injective, right? Surjective and injective implies what? Bijective, right? Onto and 1, 1 implies it's invertible. Okay. Is this fine? Everybody knows this, right? Okay. Now we need to ask this question, right? So when is this linear transformation invertible? Okay. So let's ask the reverse question. Okay. So when can we have this kind of a situation, right? Weird situation. So now I take a point here, but this point gets mapped by this as well as this. So this is something that we should avoid, right? Let me call this vector V and this is U. Okay. So V and U are different. So that means V is not equal to U, right? I should avoid this point, this situation. So let's look at what is the condition. So T operate on U, you get, let me call this as W, okay, this vector. I get W. If I operate V, I still get W, right? So that means TU is same as TV, right? What does that imply? That implies T is, or I'll take it to the other side, right? TU minus TV is 0, right? So this is same as, I'm going to write every step, but just to make sure that, minus V is 0, right? I'm invoking linearity here, okay? So be very careful. So T, U minus V is 0, right? What can you say about U minus V? See, U and V are not the same vector. So U minus V cannot be 0, right? This is not equal to 0. You agree? That means you will have this situation, this kind of a bad situation. If there is a vector, when you map it, you get 0, right? Right? Do you agree? So we need to avoid what? I mean, if T has to be invertible, the first thing that you need is it should not map a non-zero vector to 0, right? So let me write that. T should not map a non-zero vector to a 0 vector. That's the first thing that you need, right? If this happens, then you are done. So it cannot be invertible, right? So of course you should map the entire range. That's another thing, right? So you take any point, there should be a point here, right? So I mean, you should cover the entire range. That's the next thing. Okay. Now let's see what are the implications of this alone for a matrix.